sophisticated machines that carry us near the edge of space fail, they do so horrifically, plummeting to Earth with a terrifying loss of life. But the truth is, passengers have never been safer because of the brightest minds, best technology, and billions of dollars focused on preventing the ultimate disasters. Now, plane crashes on Modern Marvels. On July 18th, 1996, TWA Flight 800 was en route from New York to Paris. A 747 with 230 passengers and crew. The plane was just south of Long Island's shoreline when something went catastrophically wrong.
We were notified that an aircraft was missing, and then shortly thereafter we heard that boaters had found parts of the aircraft in the water and witnesses had seen an airplane go down.
Over the next 2 years, investigators would piece together the puzzle of TWA 800 in hopes of averting future disasters and to bring reason to the senseless loss of life. But the emotional impact often obscures the truth about these tragedies. They are extremely rare. Statistically, more people will die in 1 month of traffic accidents than in 40 years of jet travel. Governments, professional unions, and private companies endlessly struggle to keep the skies safe. Still, few tragedies elicit the dread or wound the human psyche as powerfully as the crash of a commercial jetliner. They strike at our most primal fears: heights, loss of control, and even death. They also call into question our dependence and vulnerability when the technology we trust with our lives fails. In the United States, understanding these failures is the job of the National Transportation Safety Board, or NTSB. Immediately following a plane crash, the agency scrambles a GO team to investigate the cause.
NTSB will form a number of investigative groups, and depending on the groups that are formed, they'll have a set area of responsibility that they'll focus on. Focus on weather issues. Operations group will focus on pilot training, pilot background. Aircraft performance group will focus on the structure of the aircraft.
For the teams sent to investigate TWA Flight 800, the first hindrance was that the wreckage lay in over 125 feet of water. Navy salvage teams were brought in to plot the debris field with side scan and laser sonar. But what investigators found created more questions than answers.
We see pieces from the center near the wing of the aircraft. Then we have the nose of the aircraft, and then we have a much larger wreckage area that has the fuselage, wings, and all the other surfaces of the airplane. So the wreckage isn't laid out as you would expect. It's not tail, center section, nose. It's center section, nose, tail.
The debris field confirmed that the center of the plane, just forward of the wing, had been torn from the aircraft in flight. Fueled by eyewitness testimony, the press began speculating on everything from terrorism to an accidental U.S. missile firing. So many questions were raised that both the FBI and CIA joined the investigation.
In the investigation process used by the safety board, everything's on the table when we start. We collect all the pieces of information from every source. Everything's a possibility. And then as we start going through collecting more information, areas start to eliminate themselves.
Over the next 9 months, NTSB crews recovered and transferred the wreckage to the Calverton Hangar facility on Long Island. With every scrap holding a potential clue, the investigators began putting the plane back together.
Components were identified, they were placed on the floor in a kind of a two-dimensional mock-up, I would call it, of the aircraft. And then the structures people, the metallurgists, then could look at those components and then based on where they were on the aircraft, try to piece together the failure mode that was involved during the accident sequence.
But investigators needed more and set out to rebuild 93 feet of the shattered plane. Oddly, once the reconstruction was complete, all the clues pointed not to a criminal act, but an empty fuel tank.
As we started putting the wreckage and the pieces together and doing the layout, it was obvious to our investigators that something occurred in that center fuel tank. The question is what?
The fumes in the tank had ignited, tearing a hole through the bottom of the aircraft, causing a massive structural failure. The nose section separated from the rest of the plane and plummeted to the ocean. After a brief climb taking nearly 20 seconds, the fuselage suffered another explosion. What remained of the aircraft then went into a steep dive, breaking apart roughly 5,000 feet above the water. But further questions remained.
Yes, the center fuel tank ignited and caused the structural breakup of the aircraft. Then you take a look at what are the possible events that could ignite the fuel and the air mixture in the tank. And it became a huge list of events that could have done it.
The investigation had succeeded in understanding the chain of events, but not the actual cause of the disaster. Still, there was enough information to enact new legislation. To save on weight, planes often fly with just enough fuel on board to complete the flight, which means some of the multiple tanks are regularly left empty. After the final report, the Federal Aviation Administration, responsible for regulating the industry, mandated that all empty fuel tanks be filled with inert gas to stop similar explosions from occurring. But the investigation exemplified one terrifying truth about plane crashes. They are often caused by a multitude of minor problems that combined end in one massive failure. And in some cases, the exact cause is never known.
Aircraft accidents right now are extremely rare events. For one to occur at this point in time, it literally takes a breakdown of dozens of links in that chain. Dozens of events have to line up for an accident to occur.
For early aviators, the story was quite different. And the science of accident investigation, like that used on TWA 800, wasn't even on the horizon. During the 1920s, military and small personal airplanes like the Jenny dominated the skies. The crashes, though horrific, were on a small scale, and very little remained for those interested in sifting through the wreckage.
Now, the challenge in all this, of course, is if you have an aircraft that actually experiences an accident, either the pilot survives or he doesn't. If the pilot doesn't survive, you don't really understand what went wrong and how to fix it.
By the mid-1920s, the government decided federal mandates were needed to make sure both pilots and the planes being built were fit to fly. The culmination of their efforts was the Air Commerce Act of 1926.
The Air Commerce Act of 1926 established an aeronautics branch within the Department of Commerce, which is the direct ancestor of the present-day Federal Aviation Administration. Coming out of that was the licensing of pilots, the certification of aircraft, and the licensing of mechanics. From that point on, we saw a remarkable improvement in aviation safety.
But even with the improvements, more was needed, and many safety issues went unnoticed until highlighted by national tragedies. In 1931, Newt Rockne, the famous Notre Dame football head coach, was mourned in the national press when the 10-passenger, mostly wooden airplane he was traveling in literally came apart at the seams.
The wing literally fractured and failed because of problems with the design of the wing and the fact that it had exceeded its load limit. People, I think, instantly recognized that a change had to be made in aviation. We went almost immediately, we saw these metal aircraft, which had been under development actually for quite some time. We saw these metal aircraft start to predominate in the minds of airline planners and design teams alike as the way to go in the future.
But even with metal fuselage and wing construction, flying was still a risky business. Crude instruments also played a major role in early airplane crashes. Flight navigators used maps, rulers, and newly developed radio flight beacons to plot their course. Small variations in measurements, especially during bad weather or limited visibility, could lead to tragedy. In 1945, a wayward B-25 crew flying in bad weather over Manhattan miscalculated their location. As a result, the captain flew into the heart of New York City. striking the 79th floor of the Empire State Building. The crash killed all 3 on the plane and 11 more on the ground. But small crashes were about to be eclipsed as revolutions in aviation technology put more people in the air than ever before.
2 great revolutions that occurred in aeronautics were the development of the turbojet engine, which promised you 500-mile-an-hour flight speeds, and the development of high-speed aerodynamic theory and wing design that enabled you to develop airplanes that could fly very efficiently at very high speeds.
The first commercial aircraft to truly take advantage of these new technologies was the de Havilland Comet. Built in 1949 and able to hold 36 travelers, the Comet became the world's first turbojet passenger plane. But it's also remembered for its disastrous safety record.
A comet disappeared on a flight over the Mediterranean. Then another comet disappeared. There had been other incidents and accidents of the comet involving other things, but now all of a sudden you had this disappearance of airplanes and some evidence that something had occurred to them so suddenly that the crews had been unable to convey any sort of message to Earth. Clearly, these airplanes had disintegrated. What had caused this?
By looking at the wreckage, investigators concluded that the comets were breaking up due to metal fatigue. Cracks in the fuselage formed at the corners of the plane's square windows. The fatal flaw changed aircraft design. From that point on, round windows would be designed into fuselages to eliminate stress points. But as one group of engineers looked for ways to keep planes in the sky, another group looked for ways to bring them down. For the FAA, one of the best ways to prevent plane crashes is to cause them. NTSB GO teams are always on call and must be en route to a crash site within 2 hours of being notified. Plane crashes will return on Modern Marvels. On July 11th, 1961, United Airlines Flight 859 crashed while landing in Denver. The plane had left the runway and smashed into an airport construction site. The impact tore through the bottom of the jet and left the plane engulfed in flames. Remarkably, of the 122 on board, 104 survived the crash, and more importantly, escaped a killer that had plagued aviation from the beginning: fire. Since the FAA's inception in 1958, it has worked hard at improving ways to get passengers lucky enough to survive a crash off a burning aircraft.
Many of you have noticed what's called the disco lighting or the floor strip lighting. That's been a wonderful thing to prevent people from turning down the wrong set of seats and finding that an exit wasn't there.
Countless flame tests performed over the decades at the FAA's William Hughes Research Facility led to breakthroughs in fire-resistant seats and aircraft interiors.
We have seen clearly a very great difference in design application from, say, the jetliners of the 1960s and 70s with the kind of materials they had that readily gave off those kinds of toxic and lethal clouds to the kind of materials you have in a new jetliner or a new aircraft today.
Some of the most dramatic lessons about fire and other problems, such as aircraft structural integrity, were learned from full-scale tests. These well-planned disasters helped scientists understand the forces at work during the real thing.
The Federal Aviation Administration would take an old transport airplane, they would load it with perhaps an experimental fuel or an experimental fire retardant or things of this sort, and then they would run it down a track.
One of the most elaborately planned crashes conducted by the FAA was performed in 1984 at Edwards Air Force Base in California. A remotely piloted Boeing 720 aircraft was the laboratory. The purpose of the crash was to test a new fire-retardant fuel. Crash test dummies, interior probes, and high-speed cameras were also installed to measure the forces at work and to see what might be done with future aircraft design to ensure that all passengers could walk away from a survivable crash.
Well, clearly, if we take a look at what's happening to that aircraft as it hits the ground and moves along the ground, you have to make certain that the passenger remains fixed in their seat, and that whatever violent motions they're undergoing, as violent as those will be, do not result in the connection of that passenger with something else at very high impact.
Though useful, the test was far from a complete success. The pilot on the ground was unable to accurately line up the plane before impact. As a result, the left wingtip struck first, spinning the plane sideways. Metal spikes on the crash strip used to rip open the fuel tanks also ruptured one of the plane's engines. With gushing fuel and the burning engine as an ignition point, the entire aircraft was instantly consumed in a fireball. Full-scale tests are extremely expensive, and as evidenced by this 720 test crash, difficult to control. At the drop facility at NASA's Langley Research Center in Virginia, relatively small-scale crash testing allows for some very precise measurements. The Impact Dynamics Research Facility is 240 feet tall and 400 feet long.
It can lift up to 30,000 pounds, meaning we can lift an aircraft that weight to a drop height that we need to test into surfaces such as soil, water, dirt, and crash airplanes, basically, is what we do.
Here, a Learfan composite aircraft loaded with 6 test dummies is dropped from a height of 150 feet.
When it gets close to impact, we blow off the swing cables and allow it to go into free flight conditions, and therefore do what it would normally do in a real crash.
The sizes of the planes being tested may be limited, but the safety information being gathered is applicable to all aircraft.
We're learning a lot from these in a lot of ways. Not just the human information, but the structural information. Taking the information and looking at it and saying, how can we change these structures so that it absorbs energy better, so it's less heavy even, you know, what kind of exotic materials can we use instead of traditional aircraft materials to lighten the structure and make it a more efficient energy absorber. The work here is to help people walk away from survivable crashes.
But not all data comes from laboratory experiments. Some of the best devices for understanding the forces involved in a crash are on board all commercial aircraft. 2 data recorders in the back of the plane are often all that remains after a real crash. They are collectively referred to as the black box.
In fact, they're both colored orange, and one is a cockpit voice recorder and the other one is a flight data recorder. The reason they're colored orange is because they can be easily identified in airplane wreckage.
First mandated by the FAA in 1969, the boxes have continually been upgraded.
The early flight recorders were very rudimentary. There was a stylus that would scratch data on a foil medium. The recorder would record only 5 parameters, that is altitude, airspeed, heading, vertical acceleration, and microphone keying. Today, we're up to 22 parameters by law. Flight recorders are able to record, however, at least 350 parameters.
The wealth of information recorded by the machines can even be used to prevent a crash. The Flight Operations Quality Assurance Program downloads data from the recorders of working aircraft to pinpoint pilot deficiencies or minor maintenance issues before they lead to bigger problems. NASA is looking to take this type of technology one enormous step forward, with a system that will not only diagnose major problems, but also fix them, while the plane is still in the air. On rare occasions, flight surfaces such as rudders and flaps, which control the plane's direction, have been known to fail. When they do, the result is almost always disastrous.
One of the greatest categories of fatalities for civilian aircraft accidents is loss of control in flight. And these are accidents in which control surfaces fail in the aircraft. And there have been accidents such as like the Sioux City, Iowa accident, where all the hydraulics failed and the pilots were left only with engines to control the aircraft.
Still in the research phase, a software program called the Neural Flight Control System quickly analyzes the damaged plane. The computerized system then engages any working control surfaces, such as flaps, ailerons, or stabilizers, and often makes them do jobs for which they weren't originally intended.
The pilot really doesn't care what surface is being used in order to make the plane move the right way. The pilot just wants the plane to behave the way it should. And so if you put the stick to the left, you want the plane to roll to the left, and you don't care whether it's the ailerons or the elevators doing the rolling for you.
Particularly dangerous for pilots is the loss of tail controls.
So we're in a simulator, and we're going to freeze all of the tail controls on this plane, the rudder, the elevators, and the stabilizer, and we're going to see how the pilot reacts to this sort of catastrophic scenario.
Okay, I'm at 2,000 feet at 210 knots on arrival, 14 miles out from the airport. About 2,000 feet, half a mile off to the right, maneuvering to line up. Nope, and I've just had a failure. I've lost all the control surfaces on the tail.
The pilot must now compensate for the loss of flight surfaces. In this case, he uses the engines to help steer the plane, a challenge for even the most experienced pilots.
On a scale of 1 to 10, this would be a 10. Without a lot of practice, it's extremely difficult to control this aircraft.
As he approaches the landing strip, the plane bucks wildly.
Throttle up. Come on, come on, come on, come on, come on. Let's go, let's go, let's go. Come on. Come on. Okay, we're over the threshold and we're not going to do it. Yep, this is going to be a crash.
The scenario is run again, but this time, the pilot activates the neural flight control system at the first sign of trouble.
With the controller, you can see now I can pitch the aircraft. It pitches up, the aircraft pitches down, responds to the stick.
The pilot uses all the controls as if the aircraft were functioning normally. It's now up to the computer to figure out how to make the damaged plane respond.
It's very, very close to finding a normal aircraft at this point. Gear down, flaps down, auto brakes are set, and this is going to be a normal landing.
In the past 20 years, over 1,100 people have been killed due to loss of control accidents. Implementation of cutting-edge NASA technology may make this type of crash a thing of the past. But better aircraft are just part of the air safety equation. Others are working to mitigate the most complicated and dangerous variable facing planes today: the pilot.
Taxi for takeoff with India.
The drop facility at the NASA Langley Research Center was originally used by the Apollo astronauts to practice moon landings. Plane crashes will return on Modern Marvels. On the night of December 29, 1972, an Eastern Airlines L-1011 was inbound to Miami. As the crew prepared to land, an indicator light on the instrument panel flashed a warning. The front nose gear had failed to lower. Within minutes, a strange series of events that began with a burnt-out light bulb would lead to the crash of Flight 401 and the deaths of 100 people.
They couldn't get the primary indication for the landing gear to confirm it was down and locked, so they had an alternate method of doing this. And that was to send the second officer, the third pilot in the cockpit, down below the cockpit into the belly of the airplane where all of the electronics are stored. There's a viewing port down there, and you can look down through that and physically view two indices that are out by the nose landing gear.
But the second officer couldn't locate the light switch to see out of the viewing port. Back in the cockpit, the pilot and co-pilot struggled to replace the instrument panel light. Inadvertently, one of them pushed on the controls and released the autopilot. Unnoticed because of the dark night sky, the plane began to slowly descend.
When the air traffic controllers called the aircraft, having noticed that its altitude had decreased significantly, the statement they used was ambiguous. They asked them how things were coming along out there, as opposed to asking them specifically, what's your altitude? And in response to that, the captain said things were fine. He obviously didn't know or didn't recognize at the time that the aircraft was no longer at 2,000 feet. And very shortly thereafter, an altitude alert went off in the cockpit, and it went beep, 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 and this immediately alerted the flight crew. They queried where their altitude was, and unfortunately it was too late. Within a second or two, the left wingtip hit the ground, and the rest is history. The aircraft crashed in the Everglades.
When a structurally sound aircraft crashes, it's almost always the result of human mistakes. According to NTSB data, pilot error accounts for 38% of major airline crashes. Making sure that the cockpit crew are aware, focused, and in control has become the holy grail of aviation safety. Training programs have proven useful. Pilots receive an almost continuous education, depending on the carrier and type of aircraft they fly. Some of the training takes place in classrooms, but much is performed in flight simulators.
Flight simulators are extremely realistic. I mean, obviously, intellectually, the pilots know they're not really in the airplane, and there probably are some slight differences, but they do get so involved in the problem or situation that's presented to them that the level of concentration is just like in flight.
The simulators allow pilots to hone their skills in all forms of bad weather and emergency situations. Some of the training scenarios come directly from real-world crashes. Hydraulic pumps pitch and shake the simulator to heighten the realism.
Today, the fidelity of the simulators is such that we can actually fully train a flight crew to fly the airplane in the simulator to the level of proficiency that will allow them to go out, and the first time they operate the airplane will be on the line with passengers on board.
But all the training in the world does little good if the pilot is unable to remain alert and ready for a potential disaster. Simple human factors such as sleep deprivation can hinder pilots from making good decisions. Long flights and changing time zones can put pilots at risk.
Research has shown some of these problems would include changes in memory, where you may have problems memorizing things, short-term memory loss. You can have an increase in your reaction time, so it would take a much longer time for you to respond. Or you may even miss a stimuli, in which we call this a lapse, when the brain just fails to respond.
Since 1980, NASA researchers have been looking into the sleep-deprived pilot problem, and some of their studies have come up with novel solutions.
In a study that we conducted, we gave pilots a 40-minute opportunity to nap while they were in the seat. We found that during this time, they were able to obtain about a 30-minute napping period. And then during the landing phase of the flight, they showed less physiological fatigue and increases in physiological alertness. So we have found that a short-term nap actually can help pilots or any individuals in maximizing their performance and alertness levels.
Other advances are being made to the instruments pilots use. Warning and pilot alert systems have been implemented to detect potential problems before they become serious. First envisioned in the 1950s, one of the most important is a device that cautions pilots when they're flying too close to the ground.
The first generation of these ground proximity warning systems or terrain alert systems, there's several names for them, largely because of their lack of reliability or number of false warnings needed improvement. The latest generation of the ground proximity or terrain warning systems are so good that false warnings have essentially been eliminated, at least in the 8 or 9 years that it's been in service. There has been no inadvertent flights into terrain.
NASA is continually refining the instruments that keep pilots aware of their surroundings. And now technology is being developed that will give pilots a much more realistic and detailed view of where they are. NASA's new synthetic vision system takes digital terrain maps and couples them with GPS technology. Pilots are given a virtual image of the outside world, even through fog or the dead of night. Using maps generated by a 2000 space shuttle mission, the system realistically reproduces 80% of the Earth's terrain.
You're over Lake Tahoe right now. This is a photorealistic database where we've taken a digital elevation model and draped aerial photography over top of it. With this technology and with this photorealism that we've got, you can see the ski slopes, you can see the mountains, you can see everything that's out there, and we can provide that technology and that capability on cockpit displays today.
Future generations of this technology may offer a totally new view from the pilot's seat.
We're hoping that we can generate these head-worn displays that will allow the pilots to look everywhere in the airplane or outside of the airplane.
That means through the floor, ceiling, and right out the back of the plane, offering pilots a better look at their surroundings than ever before. But not all crash safety advancements have been designed into the plane. Runway technology has also evolved. And these new tarmacs may help save lives when a plane comes in out of control. Statistically, to be involved in a fatal plane crash, a passenger would need to fly a randomly chosen U.S. domestic flight every day for 21,000 years. Plane crashes will return on Modern Marvels. On March 5, 2000, Southwest flight number 1455 was on approach into California's Burbank Airport. What should have been a routine landing turned into a near disaster when the plane landed too fast and much further down the runway than allowed.
The runway Burbank Airport is 7,000 feet long, a little bit less than 7,000 feet. He touched down 2,000, 2,500 feet beyond the beginning of the runway. Normally try to touch down the first 1,000, 1,500 feet.
The crew frantically tried to stop, but failed. The plane then smashed through the airport retaining fence, into the street, and finally came to rest in a gas station parking lot. Fortunately, everyone survived. Runway safety has become a major issue as aging airports are pushed to handle ever-increasing traffic. New airports are usually constructed on the outskirts of cities, where open space is not an issue. But older airports tend to be surrounded by the cities they serve, with little or no room to lengthen a runway when necessary.
One of the things we've seen before is some type of arrestor system at the end of a runway to help slow the aircraft if it does go off the end. And this is certainly beneficial for airports like Burbank. They have short runways.
Since 1982, overruns have led to 23 fatalities, over 300 injuries, and millions of dollars in aircraft damage. A newly developed device called the Engineered Material Arresting System, or EMAS, may put a stop to these types of plane crashes. Made from porous concrete, the material lines a shallow pit, or is manufactured into small blocks at the end of a runway. As demonstrated by this full-scale crash test, performed in 1996 for the 727, the plane hits the material, sinks in, and skids to a halt. Other runway hazards exist. Increasing air traffic means the very real danger of planes crashing into each other on the ground.
Runway traffic. Runway traffic.
NASA's runway incursion prevention system is being developed to help pilots keep track of the ever-changing airport landscape.
Each airplane is equipped with broadcasting information, giving each airplane that is in the airport environment an awareness of where that other airplane is. That information is then correlated or coalesced into an onboard database and presented to the pilots on their displays. And then the algorithms that are behind that are always checking and verifying whether there's a potential that the two airplanes could come in collision.
Runway conflict. Runway conflict.
Ground thrust flaps 20. Coming to 20. Good, sir. Okay, I'm going to start a right-hand turn here. Get out of his way.
Weather can also pose a threat to airport traffic in the form of turbulence. As planes slow for landing, they become less stable and more vulnerable to atmospheric changes, but turbulence can strike at any time. Weather radar systems, originally developed during the Second World War, have steadily improved Today, through their familiar green, yellow, and red display, they show pilots the safest path through a tumultuous sky.
But also there's an added color of magenta which shows you the areas of turbulence. Today those regions can be highly exaggerated and not necessarily tell you where hazardous turbulence is.
This new radar system, being installed in the nose of this NASA research aircraft, may help future pilots find turbulence before it finds them. Over the course of 13 flights in 2002, NASA researchers took their 757 and went looking for what most pilots spend their entire careers trying to avoid.
Okay, this is going to keep up for a little while.
During our turbulence flights, we would take the aircraft in turbulence environments, and I would guide the aircraft towards thunderstorms.
We're a weather research flight, and they want to go down to a lower altitude and penetrate that weather for data purposes.
You guys have fun. God bless you.
Yeah.
Let's see.
We could make predictions using the radar of the loads the aircraft would encounter when it would hit the turbulence. Then we would actually fly into the turbulence to validate these predictions.
One of the most difficult forms of turbulence to combat is actually caused by other aircraft. As planes travel through the air, invisible wind vortices are generated at their wingtips. Planes caught in these spiraling wakes can, in worst-case scenarios, be physically flipped over. Scientists are developing mathematical models to warn pilots of these unseen dangers. Here, the computer display, up in the left-hand corner, accurately predicts the invisible vortex and marks it in red.
The reason that we use a theoretical approach and predict the location of the wake for the display is because there is no one sensor that can measure wake vortices at this point in time. The technology just isn't there to put these sensors on board the aircraft for that purpose. So what we do is actually predict the location of the wake based on the theoretical equations, and we display the predicted location of the wake on the display.
Improvements in radar, turbulence detection, and runway arrestor systems are making already safe jetliners even safer. Sadly, it would take a national tragedy to show that the greatest threat to airline safety is not a force of nature or human error, but an act of terror. According to the FAA, overcrowding at airports will only get worse. It estimates that by the year 2012, U.S. carriers will transport over 1 billion passengers every year. Plane crashes will return on Modern Marvels. Throughout aviation history, passengers, lawmakers, and safety experts counted on the fact that pilots would do everything in their power to avoid crashes. The events on September 11, 2001, changed that forever. Terrorists had struck before, placing bombs on airplanes or hijacking flights to make political demands. But on September 11th, pilots were taken out of the equation at knife point, and commercial aircraft themselves became weapons. Created on November 19, 2001, the Transportation Security Administration, or TSA, immediately began beefing up security at all passenger airports. For most travelers, better security simply meant longer lines. Today the lines still exist, but they're moving faster. Here at Los Angeles' International Terminal, these passengers heading for the metal detectors and carry-on baggage x-ray machines will wait just under 10 minutes. But even this minor inconvenience leaves many frustrated passengers wondering, what do they think they'll find?
The number of prohibited items we've pulled is astronomical. Over 11 million different items we have found at our security checkpoints in our nation's airports. That includes about 1,700 guns. That includes about 60,000 box cutters. That includes 3 million knives.
Let me have your bag.
Every passenger is checked, even those who clearly pose little threat as terrorists, such as small children and the elderly.
Everyone is treated equally, and many people ask us why. Well, I'll tell you, in Connecticut last summer, we found a 67-year-old man who had a hollowed-out prosthetic leg with a 10-inch military knife inside of it. And in Orlando last summer, we had a 6 or 7-year-old boy who had a teddy bear with a gun up inside of the teddy bear.
In 2002, the TSA spent over $4 billion on airport security. In 2003, that figure jumped to over $6 billion. A large portion of that money was spent hiring and training nearly 50,000 screeners and security personnel. But even with the additional people, one of the toughest challenges for the agency came in the form of millions of checked bags. Prior to 9/11, only 5% of luggage was X-rayed. Today, thanks to some very sophisticated new machinery, every bag is screened before it's placed on board the aircraft.
One of the tools that we use here are these explosive detection units. These machines are able to screen checked baggage at a rate of about 200 bags per hour. The way the machine works here is it's like a CAT scan machine in the hospital. Our X-ray operators can look at the machines and they are able to get slices of the bag in order to determine what's inside.
If the operator sees something suspicious, the bag, such as this one, will undergo an additional search. The TSA officer swabs the contents of the suitcase. The swab sample is then placed into this machine to detect for traces of explosives. Like many of the airport security systems, this technology is kept secret, but its capabilities are remarkable.
This machine is so sensitive, it can detect traces of nitroglycerin found in hand lotion. And we even find traces of fertilizer found on golf clubs, which is pretty amazing.
Tremendous security strides have also been made on board the aircraft. One of the most important was making sure potential terrorists couldn't force their way into the cockpit of the plane.
Well, aircraft hardening certainly is at the forefront of the things that were discussed post 9/11, not the least of which was the flight deck door. If you had seen a flight deck door before 9/11 and seen one afterwards, you can definitely tell the difference just from looking at it.
In some cases, weighing nearly 90 pounds, the new doors are made from bulletproof Kevlar, reinforced with steel. The new design, which has been installed on every domestic aircraft, makes it virtually impossible for even well-armed terrorists to take control of the plane. But one of the most controversial security issues actually involved putting weapons onto the aircraft.
The Federal Flight Deck program trains pilots that have been accepted into the program to the same standard that they treat and train every other federal law enforcement officer, whether it's FBI or BATF or Federal Air Marshal. They're trained to that standard.
On April 19, 2003, 44 pilots made up the first graduating class. Part of their training was conducted using special target simulators. The video allows them to experience the adrenaline of an armed attack, while the laser pistol records the location and accuracy of each shot. As federally trained officers, the pilots have now become the last line of defense in a long and complex security strategy.
All of these things working together is our system of systems. If one of the things doesn't function the way it should, one of the other systems is going to back it up. So the program that we have put in place is build upon one level and then build upon that level and then build upon another level to ensure that our passengers traveling in the American aviation system are the safest they've ever been.
I think we've made tremendous strides since 9/11 towards safety and security. While we cannot make it 100% guarantee that nothing's going to happen on an aircraft, I can tell you that I'm an airline pilot and I fly all the time, and I've seen what goes on behind the scenes since 9/11, and it's a far safer environment today than it ever has been.
Despite the attacks on September 11th, flying thousands of feet in the air at nearly the speed of sound is still one of the safest forms of transportation. And with billions to spend and millions of lives at stake, aircraft safety professionals plan on keeping it that way.